Hi, this is Mr. Compania. Today we're going to be taking a look at the relationship between radiation intensity and distance. So today's objective is to collect data and determine the relationship between radiation intensity and distance. So as you probably already know, there are many radioactive minerals and elements out there. Here is an example of radium-226, has unstable nuclei, which means it's radioactive. So the radiation that comes off of this shoots off in 360 degrees in all directions. And it's really just a form of energy that's being emitted by this. So I'd like you to pause the video and answer the question, what does the sample of radium-226 look like to you? Does anything surprise you? Well, for me, I remember growing up watching cartoons. Anytime I saw something that was radioactive, it would be glowing in the dark or it would be green. So now we see a diagram of a radium-226 nucleus in the process of undergoing radioactive decay. So you can see it starts off as radium and it ends up becoming radon and a helium atom. And if you remember, a high energy helium atom that's whizzing by as something is decaying, it represents one type of nuclear radiation we've learned about. So for today's investigation, we're going to be taking a look at a sample of radium-226, which, as we've said, is an unstable radioactive element. It contains 88 protons and 138 neutrons in its nucleus, and when it decays, it emits alpha particles. Now, in this simulation, you will have a sample, a container of radium-226, which has about 10 to the 23rd atoms in it. You will count the number of alpha particles that are detected at certain distances. You will change the distance and you will measure the amount of radiation. Take a moment and write down, in this situation, what would be the independent variable and what would be the dependent variable. And remember, the independent variable is what was changed and the dependent variable is the thing that was changed because of that. In other words, you manipulate the thing that is the independent variable and you measure the thing that is the dependent variable. So take a moment and write a hypothesis. What happens to the amount of radiation detected as you move away from the radioactive source? Write your hypothesis below. So next we're going to use the drawing tool to sketch out what you think the graph might look like. Again, the drawing tool is located up here. And you can pick any of these to do it. A line graph might work if you feel like it is an inverse relationship. Or you could also use the curved connector here if you feel like it looks something like this. You always have the scribble tool available, so you could freehand the design that you think works the best. Let's prepare for the simulation. So this lab is an online simulation. And if you take a college physics course, you may actually do this lab with real radioactive sources. And of course, the proper safety precautions. So here's an image of your lab setup. So let's take a look at this diagram. Here it says we have a timer for how long the counter has been recording data. You can see the distance between the sample and the detector. If you click the up arrow, you're going to watch the detector move away. And if you push the down arrow, you'll watch the detector come closer to the radioactive sample. You have the detector itself, which actually detects the alpha particles. You have a counter, which is going to tell you how many alpha particles were recorded. You have the name of the radioactive sample. You have the button to reset the clock and the counter. And you have a pause button that you could really hold the clock and the counter so you could write down your data. So these numbers aren't changing on you. All right, so let's go to the site now. Click the link. It says here, Radiation Detection Lab. In this lab, you'll be looking at the amount of radiation you detect from a radioactive source based on the distance between the detector and the source. When you're ready to start the lab, click on the Begin button. Okay, and you can see immediately we've got a lot of things going on here. We have our radioactive sample. There's our radium. You could see the particles, the alpha particles actually flying off of this. Now, in reality, you wouldn't be able to see this. That's why we have the detector. Here we have the detector, including the probe. And the probe is really the part that is sensitive to the alpha particles, and that will let you know the concentrations. If we push the down arrow, you can see it comes closer. And if we push the up arrow, you can see that the probe moves further and further away. Now, if you wanted to see exactly how many counts that we have, how many particle detections we have at 80 seconds, you could just click the whole button when it says 80. Don't worry about being too precise. It's kind of tough to land it exactly. But here I stopped at 79.9. I'd say that's good enough. And now we know that we had 571 hits. Now, 571 detections. Now that number doesn't really help me much because all the while I was moving the probe up and down. So these results are not valid. So what I want to do is click the reset button, get me back down to 0, and you'll notice that it immediately starts again. And if I click reset, that just brings it back to 0. So let's jump back to the diagram on the previous slide for reference. What color is the container holding the radioactive sample? You have 3 more questions, try to answer those, and we'll move on. So if you're feeling confident using the simulation, move ahead a couple slides and complete the independent work. I do have another video where I model the simulation, so you can look for that in case you're a little bit confused. I hope this was helpful. Thanks for watching.